Alright, Year 12, let's finish chapter 13, dynamics. 13G is about vector functions. The main equation that will be using will be the Newton's second law. You have your vector equation. We also will use vector function notations to solve dynamics problems, and we'll focus also on motion in a straight line. So first example out of two, you have your forces that are applied, you have the mass of the particle, and you have three parts of the question. First part is find the acceleration, second part is the position as a function of time, which also be a vector function, and finally the Cartesian equation of the path of the particle. So pause the video, have a go at solving part A and B, then if you have a little bit more time, part C, and we'll come back in a minute. Alright, for part A, you just apply Newton's second law, you determine your resultant force, so it's the sum of the two forces, you rearrange and group the I and J component. We then make, using the Newton's second law, make A the subject, so it's the resultant force divided by the mass, and we get this expression. Again, you need to verify your work, as for part B you're going to need that correct expression of the acceleration, which is constant. So for part B, to determine the position, you will have to anti-differentiate twice to get first the velocity from the acceleration and then the position vector. This is the expression of the acceleration, which is the derivative of the velocity. So then we anti-differentiate in terms of t. We end up with a constant as we anti-differentiate. As we're doing that in 2 dimensions, that constant is actually a vector. You use the precondition at t equals 0, v equals 0. We determine that that c constant is a null vector. So we can write the vector form as a function of t. We anti-differentiate again. We get the vector position plus a vector constant. We use the initial position, which is given here. We get the d vector as a constant vector, and we can rewrite the vector position by regrouping the terms in I and j. So what we have here is the x component, and that's the y component. So for part C, what we notice is they have a t squared in common. So using we rearrange the first equation to make t squared the subject, and we're going to substitute that into the second equation. So here's the second equation. That t squared is replaced by the expression coming from the first equation in terms of x. We expand the brackets and rearrange it, and you can see it's an equation of a straight line. Now just be careful, this is not a whole straight line. They forgot a step here. What they've done is, when you have your x expression and your y expression, you need to, looking at the t value, what would be the values of x, so that will be your domain, and what would be the values of y, so that will give you the range. So you can see they are parabolas, so that's a parabola, and the domain is, it will go from 3 to positive infinity, and here it's a negative, so it's an inverted parabola, and it will be from negative infinity to 2. So it will be actually a half line of some sort. As you have the domain and the range, it will not be a complete infinite line. So just be careful with that. Alright, last example, probably a little bit more straightforward. You have your vector position given here, you have your mass, the mass of the particle, you need to find the initial position, the Cartesian equation, and then the resultant force at a given time. So for the initial position, we just substitute t equals 0. To find the Cartesian equation, we identified your x and y, which we have. They both have a t cube. So what we do is we rearrange the first equation in t cube, we substitute into here, that gives us a equation of a straight line. As a domain and range, x, it's a cubic, so the domain is R and the range is going to be R as well, so it's going to be a complete straight line. For part C, the resultant force is using the Newton's second law, so we need to differentiate the position to get the velocity. We differentiate again to get the acceleration. We determine the acceleration value when t equals 1, which is here a fixed vector. We multiply by m, and that will give us the resultant force for t equals 1. And that's it for chapter 13. So see you later.